two of the ones that I think you might want to spend the most time on are doing some trig function rearranging in that step where you're trying to decide which method you're going to use to integrate. And it can be a little frustrating because you've got to look for a lot of things and it takes some practice. So two that are up here, the first one we've got 2 over p squared plus 16. The first time I saw it I thought, if that were 16p squared plus 16, that'd be ideal. Because if that were 16p squared plus 16, I could easily use inverse tangent here. So it'd be kind of nice. So as I'm thinking about that, one technique would be to let the p value equal 4 times the u value. Instead of picking a u value, you're actually picking what you're going to let p be substituted for. And in looking ahead, what that's going to let that become in the denominator will be 16u squared plus 16. And since they'll both have a factor of 16, when you look at the derivative for inverse tangent, you'll see that we need something squared plus 1, and we're going to be able to get there. So with this suggestion of u, not saying you'd come up with that yet yourself, then the u value is really 1/4 of the p value. Du then be 1/4 dp. We would go about setting up in our rearrange over here everything we would need to bring that in. So I'd pull that 2 out front for a minute. I'd like a 1/4 dp in here when I'm done in order to switch out for my du's. To put that 1/4 in there, I'm going to balance that with a multiply by 4 outside. And then I'm going to leave the denominator alone for a moment because until I switch to u's, nothing's going to change down there. And I don't see my u in here. We'll see that in a minute. We're actually telling p how it's going to replace right there. So as I go to do my substitution or my function rewrite in terms of u, the 1/4 dp become my du. And in the denominator, I'm going to end up with 1 over p is being replaced by 4u's, so this will be 16u squared plus 16. I can factor that 1/16 out. I'm going to bring it outside. Factoring that 16 out of the denominator of both parts of this is going to give me 1 over u squared plus 1 du. And so basically I have half. And then as I go to integrate 1 over u squared, I realize that that's inverse tangent of my u value. And so I'm just about done, and then I'm going to resub in. I've got, oops, sorry, not 1/4, 1/2. Sure I can read my own stuff. I've got 1/2 inverse tangent of, and then we've got to sub back in our u value as 1/4 p plus a constant. Is that easy to come up with on your own yet? Not quite. So for a while, they're going to give you some u suggestions with that. And the next one, as I look at that one, I also see trig because I see a square root with a 1 minus something being squared. So I'm thinking inverse sine here. And I'm thinking that since this is something being squared, I just have to figure out what's being squared there and maybe assign that to u. So what's being squared there is a 4x squared. Looking ahead, I do see that my derivative for that would be 8x dx, and I can pretty easily get that in there if I wanted to. So my goal is to use inverse sine here because I saw something down there where as I worked out my u and du, it started to work itself out. I had the pieces that I will need in order to do this. So in order to visualize my du being in here, I'm going to need an 8x up here, and so I'll need a 1/8 to balance out there. In the denominator, I'm not changing anything just yet until I change to u's because I already know my plan. And now I'm going to change over to my u's. So 1/8, the integral of my 8x dx is going to become my du. This is going to become 1 over the square root of 1 minus u squared. As I go and look, that's my inverse sine, so when I go to integrate, it's going to be 1/8 inverse sine of u. And then obviously plus my constant. When I go to sub everything back in then, my final integral, 1/8 inverse sine of 4x squared plus a constant.